Hello, my name is Teksim, and today I'll be giving a explanation about the chapter 7 and chapter 8. Uh, yes. So the table of contents today is pretty much simpler than the one comparing to quiz 2. The first one we're going to talk about chapter 7, which is called the internal forces. And the second one is chapter 8, and chapter 8 is gonna be about friction. So let's talk about chapter 7, internal forces. So the first idea that we're going to look at is the internal loading for structure members. So to design a structural or mechanical member, the loading acting within the member must be known in order to ensure that the material can withstand this loading. Internal loadings can be calculated using the method of section. And we have learned the method of section from the previous chapter, which was chapter 6. And it is also said that the force component NB, as you have seen in the picture, that acts perpendicular to the cross section is termed the normal force. So you have to keep in mind that NB is the normal force and it is perpendicular to the cross section. The force component VB that is tangent to the cross section is called the shear force. In this case, it's V for shear, and in the Schnitt-Kraftmaster, it's the Q for shear, and it is tangent to the cross section. And the last one is going to be the couple moment, MB. So MB is referred to the bending moment. So the force components prevent the relative translation between the two segments, and the couple moments prevent the relative rotation. So according to Newton's third law, well, these loading must act in opposite directions on each segment. So we were to talk about, so moving on to a different idea, we were to talk about a three-dimensional world, and y in the normal force in the vertical direction, and y is the normal force. Vx and Vz are the shear force components, and we have to also keep in mind that n is perpendicular to the cross section, and the shear force is tangential to the cross section. So my is the torsional or the twisting moment, and mx and mz are the bending moment components. So I mean the variables are going to be the same, n, v, and m, but in the three-dimensional world we have x, y, z components, so it changes based on different exercises and experiments. And for most applications, these resultant loadings will act at the geometric center. As you can see in picture B, it is in the center, and it's also known as the centroid of the cross-sectional area. So moving to, if we look at it at a two-dimensional perspective, we have shown that the three internal loadings resultants exist as the shear going down is the shear force, which is tangential to the cross section, the normal, which is perpendicular, and the bending moment. For the sign convention, the normal force is said to be positive. It creates tension, meaning that it pulls away from the beam itself, and a positive shear will cause the beam section on which it acts to rotate clockwise, and a positive bending moment will tend to bend the segment which it acts in a concave upward manner, or from what I learned, it makes a smiley face. It makes beam having a smiley face. Loadings that are opposite to these are considered negative, or the other side. So there is also an important notice that we should look at it. So it is said that there can be 4 types of resultant internal loads in a member. They are the normal and the shear forces and the bending and the torsional moments. These loading generally vary from point to point. They can be determined using the method of sections. So moving on to the next point is the shear and moment. So before talking about shear and moment, we first going to look at what are beams. Beams are defined as structural members designed to support loadings applied perpendicular to their axes. In general, they are long and straight and have a constant cross-sectional area. They are often classified to how they are supported. As you can see in the picture below, I have shown a beam of a building. So, a simply supported beam is pinned at one end and roller supported at the other, whereas a cantilever beam is fixed at one end and free at the other end, as you can see at the type of beams below. So the actual design of a beam requires a detailed knowledge of the variation of the internal shear force and the bending moment, the internal tangential to the cross-section and the bending moment. Notice the word bending in it. So the bending moment acting on each point along the axis of the beam. So as you can see below, there are many types of beams that I have listed. First one is the cantilever, which is it's fixed at the other end. The second one is the simply supported. It's a pin at one side, and the other side is the roller. The overhanging is when there are 2 rollers or pin, and there are some overhanging at the side. And the continuous, as you can see, it continues with so on. It has many supports to it, and fixed end having both a fixed support at one end and another fixed support at the other end. And the last type of beams, which is the cantilever or the simply supported, which is a fixed, and there's also another roller at the other side of it. So, shear and moment diagrams for a beam provide a graphical of how internal shear and moments vary through the beam length. As you can see from below, I have shown the shear diagram of a force applying on a beam. It is in blue, and the moment it is in red. Well, to obtain these diagrams, the method of sections is used to determine V and M as functions of X. These results are then plotted. That if the load on the beam suddenly changes, the regions between each load must be selected to obtain each function of X. So, the procedure for analysis. For the support reactions, we must first determine all the reactive forces and couple moment acting on the beam and resolve all the forces into components acting perpendicular and parallel to the beam's axis. For the shear and moment functions, we first specify separate coordinates x having an origin at the beam's left end and extending 2 regions of the beam between concentrated forces and or couple moments, or where the distributed loading is continuous. Then the section at the beams at each distant x and draw the free body diagram of one of those segments. We also must be sure that V, shear, and the bending moment are shown acting on their positive sense in accordance with the sign convention given in the topics I've talked earlier. The shear V is obtained by summing forces perpendicular to the beam's axis, and the moment M is obtained by summing the moments about the section end of the segments. So, the shear and the moment diagrams. For the shear and the moment diagram, we must plot the shear diagrams V versus X, V as horizontal and X as vertical, and the moment diagram M versus X, like the V versus X. If computed values of the functions described V and M are positive, the values are plotted above the x-axis because they are positive, whereas negative values are plotted below the x-axis. Obviously it's negative, so it's plotted below it. So moving on to the other point that I want to talk about is the relation between distributed load, shear, and moment. A free body diagram for a small segment of beam having a length delta x. So you can see in the left picture below, delta x is chosen at a point x along the beam, which is not subjected to a concentrated force, a couple moment. The distributed loading has been replaced by a resultant force F is equal to W of x that acts on a fractional distance K of x from the right end. If we apply the force equilibrium of each force equation of equilibrium to the segment, then we would find the formula, the given formula. We can use the sigma of Fy, and we find the delta V is equal to W of x times delta x, which is similar to the Riemann sum or the sigma formula. So we dividing both sides by delta x and let it tend to infinity, meaning that we take the limit of it where it tends to infinity, then we get dv over dx is equal to wx. So it is also the same as saying that the slope of the shear diagram, because the slope of something is the first derivative of that function as the distributed load intensity. Well, furthermore, applying integral from both sides to solve the equation to find delta V. Then after applying the integral, we find that delta V is equal to the integral of W of x dx, or we can say it's the change in shear. Delta V is shear, and Wx integral is used to find the area, the function Wx, the area under the loading curve Wx. So if we apply the moment equation of equilibrium about point O on the free body diagram, we would find something similar to V, but this one would be a different formula. So it would be delta M is equal to V delta x plus, this time it's plus K W of x, function of x, times delta x square, the distance square, plus, it's not minus, it's plus. I usually repeat that mistake, putting minus, because I thought it's minus instead of plus, but we should keep in mind that it's plus. So applying the same thing later on, dividing both sides by delta x and let it tend to infinity, taking the limit where it tends to infinity, where x tends to infinity, then we get dm over dx is equal to v. Well, it's also the same as saying that the slope, the first derivative of m, the slope of the moment diagram is equal to v, the shear force. And we apply the same procedure for the same procedure as the shear earlier. We apply the integral on both sides to find the area. Then we can find that delta m is equal to the integral of v dx, which is also the change in moment is equal to the area under the shear diagram. So, important notice, the slope of the shear diagram at point is equal to the intensity of the distributed loading, where positive distributed loading is upward. dv is greater than dx, and dx is equal to wx, u function of x. The change in the shear, delta v, between 2 points is equal to the area under the curve, under the distributed loading curve between the points. So, and if a concentrated force acts upon on a beam, the shear will jump upward by the same amount. The slope of the moment diagram is it's at a point equal to the shear. For example, dm is greater than dx, which is equal to v, and the change in the moment, delta of m, between 2 points is equal to the area under the shear diagram between 2 points. If a clockwise couple moment acts on a beam, the shear will not be affected. However, the moment diagram will jump upward by the amount of the moment. Points of zero shear represents point of maximum or minimum moment, since dm is greater than dx is equal to 0. Moving on, which is chapter 8. Chapter 8, we talk about friction. So, first of all, let's talk about the characteristic of the dry friction. So it is said that friction is a force that resists the moment of two contacting surfaces that slide relative to one another. This force always acts tangent to the surface and at the points of contact, and it is directed so as to oppose the possible or existing motion between the surfaces. And dry friction, which is sometimes called Coulomb's friction, since its characteristic was studied extensively by French physicist Charles Augustin de Coulomb in 1781. Dry frictions occurs between the contacting surfaces of bodies when there is no lubricating liquid. A good example of it, a friction force, is when a guy pushing a block and it's a force applied the other side and a static friction applying on that side. And if you kind of look at the friction force and the applied force diagram, we can see that for it would jump up and it would go back down, and it would be constant due to the difference because of the sliding frictions and the static friction. So moving on is the theory of dry friction. So the theory of dry friction can be explained by considering the effects caused by by pulling horizontally this way, or on the x-axis on a block of uniform weight. Yes, pull horizontally on a block that has a weight P, which is resting on a rough horizontal surface that is non-rigid or deformable, meaning that it's resting on a surface that is not rigid or deformable. So we have to keep in mind pulling on a horizontal direction. It has a weight P and it's resting on a surface that is non-rigid. As you can see in picture A below, then the upper portion of the block, however, can be considered rigid, the upper portion of it. From the picture, we can see that the floor exerts an uneven distribution of both normal force, the delta of N, and the frictional force, the delta of Fn, along the contacting surface. For equilibrium, the normal forces must act upward to balance the block weight. You can see this in picture D. As you can see, the N is moving upward in the opposite directions of the weight to cancel the block's weight, the force of it. And also the frictional forces act to the left to prevent the applied force P from moving the block to the right. So we're trying to move a block to the right. There's a friction pulling it the other way. That's why we feel the resistance when we try to pull something. And each reactive force contributes to both frictional component, delta Fn, and a normal component, delta of Nn. The thing that we have to keep in mind is N is resisting W, and the friction force is resisting the force P that we try to pull on a horizontal direction. So in cases where the surface of contact are rather slippery, the frictional force F may not be great enough to balance P, and consequently the block will tend to slip. In other words, as P is slowly increased, F correspondingly increases until it attains a certain maximum volume, and Fs is called the limiting static friction force. It has been determined that this limiting static friction force Fs is directly proportional to the resulting normal force N. And we can express this mathematically using the formula Fs is equal to the mu s times N. As you can see in table 8.1, it shows the typical values of mu s of different material. Metal on ice, wood on wood, leather on wood, leather on metal, copper on copper. And the different objects have different values on mu s. It varies from different exercises and experiments. So, moving on to that. If the magnitude of P acting on a block is increased so that it becomes slightly greater than Fs, the frictional forces on the contacting block will drop to a smaller value Fk. And Fk it's called the kinetic frictional forces. The block will begin to slide with increasingly speed, as you can see in the picture below. As this occurs, the block will ride on top of this peak at the points of contact. The continued breakdown of the surface is the dominant mechanism creating kinetic friction. Experiments with sliding blocks indicate that the magnitudes of the kinetic friction force is directly proportional to the magnitude of the resultant normal force. And we can express this expression mathematically as Fk is the kinetic frictional force, is equal to mu k times N. These are two different things comparing to the other slide, which is this one. One is Fs and one is Fk, and it has different characteristic between those two. So the characteristic of dry friction, or the summary of it. So the first thing is the frictional force act tangents to the contacting surfaces in a direction opposed to the motion or tendency for motion of one surface relative to another. The maximum static frictional force Fs that can be developed is independent of the area of contact, provided that the normal pressure is not very low nor great enough to severely deform or crush the contacting surface of the body. The maximum static frictional force is generally greater than the kinetic frictional force. Fs is greater than Fk for any two surfaces of contact. However, if one of the bodies is moving at a very low velocity, keep that in mind, over the surface of another, Fk is the kinetic frictional force, becomes approximately equal to Fs. So before, Fs is greater than Fk, but when it moves at a low velocity, a slow speed on top of a surface of one another, then Fk, it gets closer to Fs. When slipping at, moving on to the next point, when slipping at the surface of contact is about to occur, the maximum static frictional force is proportional to the normal force, such that Fs is equal to µs times n. That's simple. And applying the same concept, when slipping on the surface of contacting is occurring, one is about to occur, and one is occurring, the kinetic frictional force is proportional to the normal force, such that Fk is equal to µk times n. The formula is similar. One is Fs, one is Fk, and the varies of the value of mu varies differently depending on which objects is acting on one another. So, moving on to our chapter 8, it's the problem involving dry friction. So, in general, there are three types of static problems involving dry friction. They can easily be classified once free body diagrams are drawn, and the total numbers of unknowns are identified and compared with the total numbers of available equilibrium equations. So the first one is no apparent impending motions. Problems with this category are strictly equilibrium problems, which require the numbers of unknown to be equal to the numbers of equilibrium equation once the frictional forces are determined from the solution. However, their numerical values must be checked to be sure that they satisfy the inequality that F is lower or equal to µs times n. Otherwise, the slipping will occur and the body will not remain in equilibrium. The second one is the impending motion at all points of contact. In this case, the total force and total number of unknowns will equal the numbers of available equilibrium equations plus the total numbers of available frictional equations. F is equal to µs times n. When the motion is impending at the points of contact, then Fs is equal to µs times n, where if the body is slipping, then Fk, we use Fk instead. Fk is equal to µk times n. Moving on to the next one is the impending motion at some points of contact. So as you can see here, the numbers of unknown will be less than the numbers of available equilibrium equations plus the number of available frictional equations or conditional equations for tipping. So as a result, several possibilities for motions and impending motions will exist, and the problem will involve in determinations of what kind of motion which actually occurs. So let's look at the procedure for analysis. For the free body diagram, we draw the necessary free body diagram, and unless it is stated in the problem that is impending motion or slipping occurs, always show the frictional forces are unknown. Then we determine the number of unknowns and compare with the others. If there are some unknowns in the equilibriums, it will be necessary to apply the Fk formula. If the equation is equal, if the equation is F is equal to µs times n is used, it will be necessary to show that F is acting on a correct sense of direction. Next is the equation of equilibrium and friction. Applying the equation of equilibrium and the necessary frictions equation and solve for the unknowns. And if it involves a three-dimensional, and it's difficult, but we can do it by writing the Cartesian vectors. Wedges. Wedges is simple. A wedges is simply a machine that is used to transform and applied force in a much larger force directed at a approximately right angles to applied forces. Wedges also can be used in slightly move the heavy loads. Wedges are used to lift a certain object by applying a force to the wedge, as you can see from the picture below. So, frictional forces on screw. In most cases, screws are used as fasteners. However, in most, they are not. They are incorporated to transmit power or motions from one part to another machine. So in this section, we will analyze the force acting on the square thread screws. The analysis of other types of screws, such as the V-thread, is based on the same principle. So the upward impending motion. So it is subjected to the upward impending motions caused by the applied torsional moment, and a free body diagram of the entire unraveled thread edge is contact with the jack can be represented as a block. The force W is vertical force acting on the thread, or the axial force applied to the shaft. M is greater than or is the resultant horizontal force produced by the couple moment M about the axis. The reaction or of the groove on the thread has both frictional and normal components, where F is equal to nu case times N. After doing the equation of equilibrium, we can find that M is equal to R times W times the tangent of theta plus phi of S, phi of S. Moving on is the frictional forces on a flat belt. Whenever belts, drives, or bands, brakes are designed, it is necessary to determine the frictional force developed between the belt and its contacting surface. It is in these sections we will analyze the frictional force acting on the flat belt, and although the analysis of the other types of belts, such as the V-belt, is based on similar principles. A free body diagram of the belt segment in contact with the surface is drawn below. The moment and the frictional forces acting on the different points along the belt will vary both in magnitude and direction. Due to this unknown, the analysis of this problem will first require to study the forces acting on the differential elements of the belt. A free body diagram of the element having a length shown in the picture below is used to calculate the formula. So applying the two forces of equation, which is the sigma of fx and the sigma of y, and after finding that, we can use, we have the theta is off in decimal size, and sine of theta over 2 is equal to theta, and it's greater than 2, and it's the same procedure. Applying to that, we get mu dn is equal to dt, and from that we can use it to find T2, and T2 is equal to T1 e to the power of mu times beta. T1 and T2 is the belt tension, and the mu is the coefficient of static kinetic friction between the belt and the static contact. B is the angle of the belt to the surface contact measured in radians. E is 2.781, and so on. It's the natural logarithm. So I've come to the end of my explanation on chapter 7 and chapter 8. If you have any questions, feel free to drop it down in the comment below. And thank you for listening. Goodbye.